Okay, so let's now start a new lecture, which is lecture number 9 on symmetry and correlations, their correlation with the Bravais lattices. So before we get into it, we just want to recap what we did in lecture 8 and 7 and 8. So what we learned there was this concept of symmetry, okay, and symmetry is not something which is just on the basis of look. It is on the basis of certain well defined criteria, and we defined that there are 4 kinds of symmetry elements. First is translational, and translational is a given for every system. So translational is something which is generally not talked about when we define the when we do the classification of crystals. We don't talk about translational symmetry, because translational symmetry has to be there for a crystal for a periodic system. So translational symmetry, then we have reflection symmetry, then we had rotation, and then we had inversion. Okay. So these 4 symmetry operations basically complete the there are some other symmetry operations which are glide and skew, but these are the 4 major symmetry operations which have to be which define the crystal systems and Bravais lattices. And then there are finer distinctions between the same class of Bravais lattices. There are different materials with different motifs and different other symmetry elements come into picture, but these are 4 basic symmetry operations which define your Bravais lattices and crystal systems. And we also saw that what is the defining symmetry for various crystal systems. Okay. Now that is mostly governed by rotation. So for example, for cubic system you need to have 4 3-folds, for tetragonal you need to have 1 4-fold, for orthorhombic you need to have 4 2-folds, and so on and so forth. So we had defining symmetry for 7 classes of crystal systems, and then we looked on to Bravais lattices. What is the correlation of these Bravais lattices with the symmetry? So for example, so we were looking at we looked at 7 crystal systems. We defined them in categories of P, I, F, C, and we saw that in case of cubic you only have primitive, body centered and face centered. In case of tetragonal you had only primitive and body centered. In case of orthorhombic you had all 4 of them, and so on and so forth. So the question was why are some of these missing? So for example, why is cubic missing, C-centered cubic missing, why is face centered tetragonal missing, why is C-centered tetragonal missing, and so on and so forth. And then of course you had hexagonal, which again had only primitive system. Rhombohedral also had only primitive, and then monoclinic again had only primitive, and then triclinic, monoclinic also had C-centered, triclinic had only primitive. So we looked at the reason of, for example, C-centered cubic. Why C-centered cubic is not there? The reason is because C-centered cubic can be defined as body centered tetragonal, and C-centered cubic does not fulfill the criteria of 4 3-folds which must be present in a cube. So although it may look like a cube, it is not a cube. It has a smaller unit cell in terms of body centered tetragonal, and it fulfills the symmetry criteria of tetragonal unit cell. So C-centered becomes body centered tetragonal. Similarly, now the question arises is, why is that you don't have a face centered tetragonal? So we will not go into all of them, but I will give you some examples as to why some of them are not present. So let us say a face centered tetragonal here. So let me just draw a unit cell here, tetragonal unit cell. So we will draw 2 unit cells. So you might have guessed by now that they are not there because either they do not make a valid lattice or they convert into something else which has either higher symmetry or a smaller size. Okay. So, this is it does not look like the two are slightly different in sizes, but nevertheless. So, let us put the atoms here. These are two tetragonal cells, adjacent ones. Let me just draw this as well, and this as well. Okay. So, we are saying that why is face centered tetragonal not there? So, we draw atoms at the center of the faces, all right. Now, so we have drawn this. Here you can see that you can construct a smaller tetragonal cell in this fashion, which is actually a body centered tetragonal. So, it has same tetragonal symmetry, but a smaller cell. So, basically we prefer a smaller cell. So, if you remember, I earlier told you there are two criteria, one is the smaller size, second is the symmetry. So, in case of cube you saw it does not follow the symmetry, right. So, in this case we can see that there is a smaller cell size which is preferred, and as a result it is defined as body centered tetragonal. That is why face centered tetragonal is not present in the Brebis lattices, because it can always be represented by a smaller body centered tetragonal unit cell, and you choose a smaller unit cell as per the criteria. So, this is why FCT is not there. Why is FCT not a Brebis lattice? So, this is the answer for that. Now, you can also choose similarly you can have so in that table. Now, if you can go back to the table, you can say that this F is nothing but I. Okay. Similarly, now you can see Y is why don't we have Y is C centered tetragonal cell is not a Brebis lattice. So, you can see that it is not a Brebis lattice, because if I make a C centered tetragon, again I will have to make two unit cells. Okay. Now, if I put the atoms here 1, 2, 3, 4, 5, 7. So, these are the atoms I have put, and C centered would mean that I can put an atom here, I can put an atom here, the atom here. Okay. So, can you tell me the answer? Because you can always make a simple tetragonal cell. With the same symmetry. So, the answer is C centered tetragonal is nothing but simple tetragonal. So, that is why this does not exist. So, basically a smaller tetragonal cell. So, you can do the same exercise for example, for hexagonal system you do not have for hexagonal you can see there is no FCH, BCH or CCH. The reason for that is the moment you put body centered and face centered, you lose the 6-fold rotation symmetry. So, it no longer remains as a hexagonal. So, that is, so you can check it out yourself. Try putting an atom at the center of the unit cell in hexagonal and try to operate that 6-fold. You will see that you will lost that 6-fold. Similarly, you try to do that in face centered tetragonal, C centered tetragonal, you can see that you will lose the 6-fold symmetry. So, now the question, one more question that you can ask me is, what is the reason for choosing, for example, in cubic FCC or BCC unit cell? Over their primitive counterparts. You have seen yesterday that one FCC is made of 4 primitive lattices. What is the shape of that lattice? It is a parallelopipe, right? It is not a regular shape, cube shape or something like that. So, the reason why you choose FCC over the primitive counterpart is because FCC has higher symmetry. In cube, you can make it, it has higher symmetry elements, it has 4 3-folds, 2 folds and 4 folds, whereas if you choose only the primitive ones, you will lose some of the symmetry elements. So, that is why FCC, although it is a bigger unit cell than the primitive unit cell, so higher symmetry despite larger size. Same is true of BCC, same is true of any other non-primitive structure which is chosen in comparison to a primitive structure. Now, another last thing that I want to tell you is that you can see you have a FCC unit cell. If you draw a FCC unit cell, it will look like this. The question that I want to ask you is that, can this FCC be represented as body centered tetragonal? For example, if I draw a neighbor to it, this is a neighbor, right? Okay, let me now color this thing. Okay. So, for the sake of representation, I can draw this atom as different. This is body centered tetragonal. So, question is, why can FCC not be represented as a BCT lattice, not in itself, as a lattice? So, you can see, now you need to see the symmetry. FCC has 4 3 folds, it has 4 folds, so 3 4 folds, and it has 6 faces, so 3 4 folds, and it has 6 2 folds. In case of tetragonal, you have 1 4 fold and 2 2 fold. So, although BCT has a smaller size than FCC unit cell, the symmetry of FCC is higher. So, since the symmetry of FCC is higher, we choose a higher symmetry. So, when you have this conflict of symmetry, then symmetry prevails. When the symmetry is similar, then you choose the smaller size. Okay. So, these are the two defining criteria. One is size, second is symmetry, and symmetry prevails over the size. Okay. So, this is the first criteria, and then this is the second criteria. So, now you can see, we have seen why do not we have 28 Bravais lattices, why do have only 14 Bravais lattices, and the reason lies in symmetry, that some of them can be represented either by higher symmetry structures or by smaller size unit cells, or in some cases they do not represent the symmetry of the crystal system at all. For example, in hexagonal system, if you try to draw C-centered or F-centered or I-centered unit cells, you tend to lose the symmetry, defining symmetry of the crystal system itself. So, these are certain considerations that we take into account when we talk about the crystal systems and symmetry. So, I hope now there is some clarity on why is there a why do you have 7 crystal systems which are defined on the basis of symmetry. Each of these has a defining symmetry, and it is the combination of symmetry operations which defines in which class a particular shape will belong to, and the choice so as we said in the beginning, you have multiple choices of unit cells, you still choose a smaller unit cell, you still choose a unit cell which is highly symmetric. So in the primitive cell, so now it is clear. So if you look at this, for example, as an example, this 1D 2D lattice. So here you can see now that we choose this unit cell in preference to either this so 1, this is 2. So 1 is preferred over 2 because of higher symmetry. Okay. And this is nothing but the combination of, so here rotational symmetry plays an important role. So that is one very important symmetry. Translation we don't talk about, because if a lattice is there, it has to have a translation symmetry. If it does not have translation symmetry, the whole chapter is closed. We do not talk about symmetry at all. So so let me now summarize the whole crystallography in a few minutes. So what we did was, we started with point lattice. Okay. Point lattice is nothing but regular array of points in a space with each point having identical neighborhood. So regular array of points with identical neighborhood. Then we defined within the point lattice, you can define a unit cell, right. Unit cell is defined as the smallest repeatable unit which can be translated into the lattice without creating any gaps. Okay. So, for example, this is now we choose this as a unit cell, or we choose some other shape as a unit cell, but we do not choose, for example, this as a unit cell, right. If you choose this as a unit cell, then this would be the repeating unit. So, you will leave these gaps in between. So, there should be no gap at all. So, that is why if you look at the rotation symmetry, there are certain operations which are, so you can see that two-fold rotation, you have filled space, right. So, if you have rectangles lined together, these are rectangles, rectangles have two-fold symmetries, right. This is a rectangle. So, all these rectangles will fill the space, there are no empty spaces. Three-fold rotation, again you will fill the spaces. Now, of course, this will make a hexagonal symmetry, but you can see in the case of cube, for example, right. So, all these will fill the spaces, three-fold and six-fold, right. Again, space filling. So, space filling is an important criteria. Okay. If you look at four-fold, the squares, all of them will fill the space. So, when we talk about three-fold, you talk in the context of, for example, cube. Okay. Three-fold you can't talk in cubic, because triangles do not fill the space in a regular fashion. Triangular lattice, because one lattice is upside down, second is upside up. So, as a result, you do not talk about the triangular lattice. So, these will fill the space, four-fold will fill the space filling. However, when you look at the pentagon now, so you look at the pentagon, you try making a pentagon now around it. So, you will see that if you try making a pentagon like this, so you will see if you create pentagons, regular pentagons will not be able to fill the, so you will have some gaps. Okay. Now, these angles, of course, around the angle, around a point you need to have 360-degree completed, and since each of these angle is how much? This is 72, this is 72, another pentagon will give you 72. So, it does not make a multiple of, so 72 into 3 will give you 216. If you add another 72 to it, it will give you 8, 288. So, if you add another 70 to it, it will give you 360, but you can't have 5 pentagons sitting around a corner. So, if you try building, now this is one, if you try building around it, this will go something like that. So, you leave a gap here. Similarly, if you try to do the same exercise on other points, you will try leaving gaps. So, pentagons do not fill the space. So, there are gaps. So, there are gaps in the structure with pentagon filling. And hence 5-fold is is not found in crystals, in periodic crystals, because there is no space filling, you leave gaps in the structures. Okay. So, this was another thing which has to do with the, and then we looked at lattice parameter, the concept of lattice parameters, which is A, B, C, alpha, beta, gamma, and correlations between these are dependent upon the crystal systems and Bravais lattices. Then we looked at what is primitive and versus non-primitive lattice. And then we looked at what is the concept of motif. This is a very important thing, motif of basis, because motif of basis will eventually determine how big a unit cell will be, what kind of symmetry will it follow, and we have not seen about it, but what kind of space and point group will it have. So, this is a very important concept. And then we moved on to the concept of crystal systems and Bravais lattices. So, you have 7 crystal systems, you have 14 Bravais lattices. We have seen why do not we have 24. There are possibilities are P, I, F, C. So, if you multiply 7 into 4, it should give you 28, but we have only 14, and the reasons lie in symmetry. So, we saw the symmetry operations, and we saw that depending upon the defining symmetry of the crystal system, you choose a unit cell which is either smaller in size or it has higher symmetry, and based on those considerations we come up with only 14 Bravais lattices. We do not have 28 Bravais lattices. So, this is sort of a short primer on crystal systems, Bravais lattices, symmetry, and in total on crystallography as to how atoms are arranged in a crystal, and why are they arranged in this in such a fashion, and how can you classify them in different classes. There is something which leads further from this is a space group and point group, but we will not consider that in this class. It is beyond the scope of this, but if somebody is interested, he or she can look at the books which can give you more information on. So, on space and point groups. So, any elementary book on crystallography will give you a knowledge of point groups and space groups. So, point group and space groups are basically further classifications of crystals. So, within one crystal class, let us say within the cubic crystal class, you will have various other connotations depending upon how atoms and molecules, I mean most of these are not single atoms, okay, most of the materials are compounds. So, in compounds, how motif arranges itself at various sites will be determined by will determine their arrangement, and this will give rise to us, they can be classified on the basis of point and space groups. So, we'll leave this out of discussion for this class. We will now move on to next topic, which is on Miller indices, which is a way to classify crystals and understand their various properties. Yeah.